So good afternoon, everyone, and welcome to the new season of our webinar cycle, Data Science and Statistics webinar, DaSSWeb. This is already our fourth season for an endeavor that started during the COVID times. This looks like long ago now. And today we have the honor and the pleasure of welcoming Peter Ruscio, whom we want to very much thank for his availability to share his recent work with us. Peter Ruscio is now Emeritus Professor at KU Leuven in Belgium. He started his career in Zurich at DTH, where he had his PhD, which led to a book on influence functions. Later, he has also been professor at Delft University of Technology in the Netherlands and at University of Antwerp in Belgium. This was before being for more than a decade a researcher at Renaissance Technologies in New York. After that, he returned to Belgium, where he stays until now. Peter is most well known for his work in robust statistics, and we do to him a lot of creations, including least stream squared regression, minimum covariance determinant estimator, the K-medoids clustering method, and the silhouettes graphical display, which most of us use currently. All this work has led to 3 books and over 200 papers on theory, algorithms, and applications, which enjoy together over 115,000 citations. Peter is elected member of the ISI and a fellow of IMS and American Statistical Association. For his work, he was awarded the George Box Medal for Business and Industrial Statistics, the Research Medal of IFCS, the International Federation of Classification Societies, the Frank Wilcoxon Prize, and twice the Jack Uden Prize. Recently, he received this year the ASA Nutter Distinguished Scholar Award for Non-Parametric Statistics. And among his PhD students, we know Annick Leroy, Rick Lopwa, Gert Molenbergs, Christoph Crooks, Mia Hubert, and Stephen Van Elst, and Tim Verdonk, and Jacob Raymakers. People's recent work is about robustness to cell-wise outliers, and this is what he will talk to us today on robust principal components by Casewise and Cellwise weighting. Peter, thank you so much for joining us today, and the floor is yours.
Thank you, Paula, for this very kind introduction. I'll switch. I'll try to I'll try to share my screen. Oh, I'm not sure that this is working. Do you see my screen now?
Not yet.
Not yet.
Oh, okay. Then I have to try this again.
So,
Share. You see it now?
no. The green button.
The green button. Yes, it says share screen.
Yeah. And then you have to choose what you want to share in your screen.
So it says one participant can share at a time, so that's okay. Advanced sharing options. Who can share all participants? So it seems like all the options are okay, but still it's not sharing. Interesting.
I think you have to click again in sharing once the screen to be shared is chosen.
So I'm clicking on share screen and then, okay, now it says share. Do you see the screen?
Yeah, good.
Yes.
Okay, great. So I think now I see the whole screen. Right.
Perfect.
So as you said, the topic of the talk is about robust principal components by Casewise and Cellwise weighting. And this is joint work with Fabio Centofanti from the University of Naples and Mia Hubert from the University of Leuven. So First, a very short introduction about what are outliers. An outlier is a piece of data that does not follow the pattern suggested by the majority of the data set. Most of the time, we consider outliers as undesirable errors that can hurt our data analysis. But sometimes they are actually valuable nuggets of unexpected information that may lead to inventions and patents. In any case, we would like to identify the outliers, which in statistics we call outlier detection, but it also has other names. In data mining, it's called exception mining. And in machine learning and data science, people talk about anomaly detection. This is a very popular name nowadays. And there are several approaches to this anomaly detection. The one we follow is that of robust statistics. This is a way to fit the majority of the data first. And then afterwards, we can detect the outliers quite easily by their deviation from that fit. And deviation could be the residual of a regression model or the distance of a covariance model and so on. There are many possibilities. So there are different types of outliers. And today I'll talk about data that do not have a response. So we have a data matrix X with n rows, which are the cases, and p columns, more than one column, which are the variables. That's our usual way in statistics to represent the data. And these data can, of course, contain outliers. Outliers used to be always in the sense of Tukey and Huber, namely thinking about case-wise contamination. So that assumes that some of the rows of the data matrix have been replaced by arbitrary rows. And such outlying rows, they may be cases that belong to a different population. There are many robust and equivariant estimators that have been developed by many people, including myself, for frameworks of covariance estimation, regression, principal components, and many other statistical models. All of these methods proceed by downweighting or even dropping outlying rows from the data. And they all require at least 50% of clean rows. This is a theorem about the breakdown point, actually. But more recently, the focus has been on a different type of contamination model, namely the Cellwise contamination model, which existed in the folklore, but the first actual publication in which it was formulated is only dates back only to 2009 in the Annals of Statistics. This was a paper by Alcalaf, Van Aalst, Johai, and Zamar. And this model assumes that some of the cells of the data matrix have been replaced by maybe arbitrary values. So this is a very different situation. And if we would downweight or drop an entire row each time that only one cell is outlying, then we would lose a lot of information. And in fact, if the number of dimensions is high, it's quite possible that every row contains an outlying cell somewhere. And still we want to be able to analyze these data. So here's a picture that shows a simplified version of this paradigm. On the left, we have the case-wise or row-wise paradigm. Gray means clean and black means contaminated. So here we imagine that 3 out of 15 cases are contaminated. So these 3 rows are not from the original population, let's say. On the right, we have the other paradigm, the cell-wise outlyingness. Now there are some black cells anywhere in the data matrix. And in fact, there are fewer black little squares on the right here than on the left. But they create a lot more problems because they contaminate a lot of rows. And in fact, only 4 out of the 15 rows are entirely clean. All the others contain one or more outlying cells. So this is difficult to deal with, and we cannot use the row-wise robust methods because there is not a majority of clean rows anymore. So the image on the right probably reminds you of the issue of missing values. That's when some of the cells are empty. We don't know what value was observed, or we didn't record that value. But here the problem is much harder because when you have missing data, at least you know exactly which of the cells were missing. But for outlying cells, nobody tells you which of the values are unusual. So you have to figure that out as well. And so the first problem really is how to detect which cells are outlying. And there are different methods for that. The oldest approach in the paper by Agostinelli, Leung, Yohai, and Zamar in 15 was to consider each of the columns separately and then to say whenever a cell is outlying in that column, then we consider it an outlying cell. So that means that you only look at the cells that are marginally outlying. They're outlying in their own variable. And that is not quite sufficient. So we can see that in this bivariate toy example, the majority of the data points follow this nice little pattern that we see here. For instance, data point number 1 is one of them, and it behaves quite well. And data point number 2, however, it is a marginal outlier in the second variable. So x2 is the second variable, and we have this horizontal little dash for every vertical coordinate. And we see that the vertical coordinate of case number 2 here is very different from the other vertical coordinates. So this is a marginal outlier. Point number 3 is marginally outlying in the first variable in x1, because we see it stands out a lot. But the problem now is number 4. Point number 4, we see that in the bivariate sense, it is an outlier, but it's not a marginal outlier. So its x1 coordinate is not really special. It's somewhere here. And its x2 coordinate is not really special either. It's somewhere here. And so we would not detect this point if we only looked at the marginals. And there is another problem right now for this point that we cannot tell which of the cells is outlying. Is it the first cell? That would mean that the point was supposed to be here somewhere and that the first coordinate is wrong. Or it could be that the point was supposed to be down here and its second coordinate is wrong. So we cannot decide whether it's the first cell or the second cell that is an outlier. And this is not identifiable. Based on these data, no method would be able to tell you which of the cells is outlying. However, if we had a lot more variables, say we have 10 variables in all, then maybe we can tell which of the two cells is the outlier, because maybe for one of the coordinates, it matches all of the remaining cells in the other 8 variables based on the correlations between the variables. And so then maybe we are able to tell which cell is outlying. So sometimes dimensionality can be, high dimensionality can be a blessing rather than a curse. So today we will not be talking about estimating location or covariance or fitting a regression. We are looking at dimension reduction here. And this is a situation where we need dimension reduction. We have an n times p matrix X containing all of the cells xij, and which corresponds to n cases that are the rows in this matrix. And we see that this particular matrix has a lot more columns than rows. So P is bigger than N. So we clearly are in a high dimensional situation. And some methods would not even work if you have more variables than cases. But certainly PCA would work. So this is a situation where dimension reduction is useful. In general, the formula, the problem is to approximate this data matrix X by another matrix X hat that has a lower dimension. So the data would belong to a lower dimensional space where the lower dimension Q is less than P and often much less than P. The model for dimension reduction is the usual one. We replace X, or we say that X is written as an X naught. So by X naught, I mean the 0, which is a superscript here, plus a term that corresponds to the center of the data, plus an error term that could contain, for instance, Gaussian noise. And in this formula, the X naught is an n times P matrix of a lower rank. The rank is Q, which could be far less than P. So this is the usual way of writing it. We will use an equivalent formulation that looks quite similar, except that X naught is multiplied by a matrix P. And P is an orthogonal projection matrix of rank Q. By orthogonal projection matrix, we mean that it's a symmetric square matrix, so the transpose is itself, and also P squared equals P, because if you project twice, you end up in the same place. And the condition, the constraint is that the rank of P is only Q. So it's a P times P matrix, but its rank is much less than P. And so we project X naught on itself. That means X naught times P is X naught. Why do we formulate it like this? That is to have a mathematical expression of this lower dimensional projection. So the image of such a projection matrix is a Q-dimensional linear subspace. By linear subspace, I mean that it passes through the origin, and we denote it as pi naught. So this 0 indicates that it passes through the origin. And the predicted data points, they are xi hats. They are the corresponding xi naught plus the center mu. They all lie on the principal subspace pi, which is parallel to pi naught, but passes through this center. And we write it like this because any Q-dimensional linear subspace pi naught determines a unique projection matrix P. And so therefore it has to satisfy the constraints that its rank is Q, its transpose is P itself, and P squared is P also. And any such projection matrix P determines a unique subspace pi naught. So dimension reduction is equivalent to finding a projection matrix. And it will be very convenient to write the problem as in the search for a projection matrix. In the classical situation, the classical dimension reduction is, of course, PCA. And there, the problem is you can write it like this with the Frobenius norm. And the usual way to formulate it is saying that we are trying to minimize the sum of squares of the observed cells minus the fitted cells, under the constraint that the fitted cells satisfy the model. And this is the sum over all of the variables and over all of the cases. And this can also be written as the double sum of the squared residuals, where the residual is just the observed cell minus the fitted cell. And the typical way of solving the classical problem is to take the covariance matrix of X, which is, of course, singular, and then compute its eigenvectors and eigenvalues. Or we can compute the singular value decomposition of the data matrix minus its average. These are two equivalent ways, and both are very fast to compute. But of course, that works fine only when the data are clean. And in reality, there can be all kinds of things wrong with the data. For instance, we can have cell-wise outliers. So the colored cells here have values that they should not have. Of course, nobody is going to tell us which cells they are. We have to figure that out. And we can also have row-wise outliers, like this row should not be there at all. And row-wise outliers is the same as case-wise outliers. We will use both of these terms interchangeably. And then to make it even worse, we can also have missing values. So the white squares here means that we do not have a value that was measured there. So this is a very realistic scenario. There are a lot of data have these properties or can have these problems, and therefore we need a method that works in such a general situation. There has, of course, been work on robust principal components, robust principal dimension reduction. These are some of the methods. There is spherical PCA. There is projection pursuit PCA. Some work on this was done in Portugal, actually. And there is the ROBCA method that we developed in Leuven. What does this method do? It first searches for an outlier-free H subset of the data. So a subset of the data with H cases, where H is between half of the sample size and the sample size. And to find outliers, we use the Stahel-Donoghue measure of outlyingness. I do not want to explain what that means here, but we find the subset that we think contains no outliers, and then we apply classical PCA to that subset. This means that we have hard weights for the cases, weights Wi, that are either 0 or 1, nothing in between. And this method works great if you have row-wise outliers, but when you have outlying cells in more than half of the cases, it may no longer work. Of course, when this method was developed, we weren't thinking yet about cell-wise outliers. So there is a final step that happens in ROBCA after getting the lower dimensional subspace. We know that in that subspace, there may still be outliers inside of it. And for that, we use a robust covariance estimator, such as the minimum covariance determinant method. That is quite old. That looks for a subset of H points whose sample covariance matrix has the lowest determinant. So the definition is actually the name of the method. And when we have that H subset, we put mu hat equal to the average of that subset, and sigma hat is proportional to its covariance matrix. It's proportional because we have to make it a little bit larger, as the covariance matrix of a smaller subset would be too small. So there is a consistency factor that depends on H. This is a simple example where the data in the subspace is bivariate. Most of the points follow this pattern, but there are 3 outliers here. And the classical covariance matrix yields this red tolerance ellipse, which is quite wide because it wants to include the 3 outliers. The MCD tolerance ellipse is much more narrow and fits only the majority. So after computing the MCD, we can then compute what is called the scores distance of each case, which is like the Mahalanobis distance, but not relative to the mean and the classical covariance. Instead, it's relative to the robust estimate of location and the robust estimator of scatter. And the eigenvectors of this robust scatter matrix then determines the principal axes that ROBCA will put out. So that's for the row-wise robust methods. There are cell-wise robust methods too, but they were not designed to be robust to row-wise outliers. One of the earliest is by De La Torre and Black in the engineering literature. Marona and Yohai proposed the method, and more recently, also in the engineering literature, is the well-known method of Candes. So the method of Marona and Yohai is closest to the kind of work that we do. So this is the one we illustrate. We actually minimize this objective function And if you look at it, it's quite similar to the classical objective function. If this row function would be just the square, and then the scale estimates would cancel, and we would just get a double sum of the squared residuals, which is the classical PCA objective. By inserting a bounded row function, Barona and Yohai turned this into a cell-wise robust method. They apply iteratively weighted least squares to an initial estimator that is the hardest part, to find the initial estimator, and the initialization is based on successive fits of rank 1. This method is also able to deal with missing values, but it has a big problem, which the authors already mentioned in their original paper, which is that it finds too many outlying cells that are not really outlying, and this is due to an issue of instability. So in some sense, there are not enough constraints being used, and the solution set is too big. Then, of course, we looked for methods that are both robust to outlying cases and outlying cells. And this is what we proposed 5 years ago, the macro PCA method. It appeared in Technometrics. It consists of several steps, more or less ad hoc. The first step is to detect cell-wise outliers by a very different method. And this is the DDC method called detect deviating cells. It is able to detect some cell-wise outliers and to impute them, and also to impute missing values in a rather robust way. After doing this, we search for an outlier-free subset, as in the ROPCA method. And then we iteratively apply a PCA to that subset. And along the way, we find better and better imputations for the outlying cells and for the missing values. It works rather okay, but there are some disadvantages. There is no objective function that's being minimized, and therefore there's no theory about influence functions or asymptotics, and in particular, we do not have a very high efficiency. Also, the other issue is that the method is not as flexible, because the lists of inlying rows and the list of inlying cells are determined in the very beginning, and they cannot be changed along the way. So during the algorithm, we cannot update those lists. So there was a need to try to find a more refined method with an objective function, better efficiency, and more flexibility. And that's the topic of today's talk. This is the newly proposed method, which we call CellPCA, and we put it on archive only a month ago. So it's very fresh. Here we approximate the original data matrix again by fitted x hat, which has the same form as before, but now obtained by minimizing a single objective function, which looks quite complicated at first, but I'll explain it step by step. Starting from the inside, the innermost term here is the residual, the observed cell minus the fitted cell, divided by a scale estimate, to which we apply a row function, row 1. So this is already a replacement of the squared residual that we have in the classical method. Now it's a bounded row function that we apply. We then undo the scale, or we compensate for the scale, and we add this up over all of the cells in the same case. So J goes over the cells, and I is the case number. And there is another factor here, which is Mij. Mij is only a missingness indicator. So it is either 0 or 1. It is 0 when that particular cell is missing, because then we cannot compute this, and so we multiply it by 0, and it's 1 when the cell is being observed. We then standardize by the sum of the missingness indicators over all of the cells of the same case, And then we divide by the second scale and apply the second row function row 2. And then we again compensate for the scale and so on. So starting from the inside, we first deal with outlying cells. And then once we have added over all cells in the case, we compensate or reduce the effect of outlying rows. So we have the cellwise residuals that are the difference between xij and xij hat. And the whole square root here, we call the row-wise total deviation, the TI for the T for total. So that's total deviation of the ith cell, the ith row, the object or case number I. For the functions row 1 and row 2, we use an old type, the hyperbolic tangent type, which has a certain optimality property and which is especially useful in this particular setting, and I will explain why in a moment. So in the middle, the row function is quadratic, so it looks like the square. Then it doesn't go up quite as fast as the parabola. And then outside of a certain region, the row function stays constant. Its derivative, its psi function looks like this. It's linear in the center, which creates good statistical efficiency. Then the psi function goes down again. That's why we call it redescending. It descends after ascending. And then outside of this big central region, the psi function is entirely 0, which indicates that far away outliers will not have any effect anymore. So this is again the same objective function. Now we write it as a function of the unknowns. X is known, but the other arguments are not known, and we will try to determine them by minimizing this objective. If we had for row 1 the function z square and for row 2 the function z square, everything else would cancel, the scales would cancel, and so on, and we would just get the objective of the classical PCA. So this is a generalization of the classical PCA objective, and we get robustness because of the boundedness of our two functions, row 1 and row 2. So the boundedness of row 1 takes care of the cell-wise outliers. The boundedness of row 2 takes care of the row-wise outliers. And it is very good that this function row 1 already diminishes the effect of outlying cells. If it would not do that, then we would then a row with one outlying cell could already be flagged as row-wise outlying, and that's not what we want. So there are two sets of weights because we have two row functions. I'll start with the one at the bottom here, the row-wise weight, because this is familiar to everybody in robust statistics. The weight, the row-wise weight, R stands for row and I for the case number. The row-wise weight is just the psi function of the standardized T divided by its argument. Weight is always psi of x divided by x. So that's the same situation here for all the cases. And this weight function has the nice property that the weight is exactly 1 in this large central region from minus b to b. And usually this region will be such that over 2/3 of the data are inside. So most of the cases will have a weight of 1, will have a full weight. And then the weight goes down smoothly for this ratio between B and C. And so weights in between 0 and 1 are possible. And then outside of the big range, the weight is 0. So we will not give any weight to rows that are totally outlying. So using row-wise weight is very common and goes back to Huber's 1964 paper, actually. But what's new is that we also have cell-wise weights. So WIJC, the C stands for cell, That is the psi function applied to the cell, again divided by its argument. So we will have both row-wise weights and cell-wise weights, and that is very helpful in interpreting the results. I will not describe the algorithm in any detail, but just say that it starts from the macro PCA method that was already robust against outlying cases and cells, but not very efficient. And then it computes the scale factors, and then it takes iteratively reweighted least square steps. The algorithm is actually quite complicated because there are gradients being computed with respect to all of the unknowns. So there's a lot of computation going on. And the question for such an algorithm is always whether it converges or not. And fortunately, yes, it does converge, because we can prove that every step of this iteratively reweighted least squares decreases the original objective function. It's a complicated proof, but it's correct. And inside of the proof, the crucial property of the row functions is that rho applied to the square root of z is a differentiable and concave function. And we have plotted this function here for the row function that we use, the hyperbolic tangent version, and we see indeed that it is exactly concave and very smooth. So it's a differentiable function that is concave. That makes the whole algorithm work. Because we have a nice differentiable objective function, we can compute all kinds of derivatives. And because of that ability, we can now actually compute influence functions. What we used to call the influence function, we now call the row-wise influence function. That's the one that goes back to Hampel's PhD thesis and the book that we wrote with 4 authors in '86. This row-wise influence function can be computed for this particular method. And it's an influence function applied. What is the functional that we try to find the influence on? It is this projection matrix. So we compute the influence of an outlying case on the projection matrix that the method finds. Then there is also the notion of a cell-wise influence function that was introduced in the same 09 paper that started the Cellwise area. And so far we are yet actually the first people to be able to compute that Cellwise influence function for this particular, for this estimator. And here is an example. We had to find a very small example in order to be able to plot something. The data are bivariate, so p equals 2, and the clean data before the outlier is bivariate normal with center 0 and with a correlation of 0.9. And we are trying to fit a one-dimensional principal subspace, so Q is 1. Because the data are bivariate, we can actually plot the influence function because the argument is bivariate. And now we have to look for a univariate response, and that is the first element, the first entry of our projection matrix. We, of course, also have the formulas for entries P12, P21, and P22. But we only plot here the influence of an outlying case on P11. And we see that we obtain this smooth influence function. We also now have the cell-wise influence function, which is quite interesting. And in both of these influence functions, we recognize the shape of the psi function of the row functions that we are using. And for the row-wise influence function, we see that it's actually unbounded, but the region where it goes up is exactly on top or of the fitted subspace. So this is what happens for what we call the good leverage points, the points that are outlying but fit the model perfectly. And this is the same situation as for high breakdown regression estimators. They have an unbounded influence function, but it's only unbounded where the good leverage points are, those that actually do not harm the fit, but improve the fit. The Cellwise influence function is quite different, has a very different shape, and we see that this one is bounded. From this, we can conclude that the effect of an outlying cell on this particular estimator is not as harmful as the effect of an outlying row, or is always bounded, so the effect is always smaller. Because we have the row-wise influence function, we can repeat the usual reasoning based on central limit theorem that shows that the cell PCA method is asymptotically normal. So this is the estimated projection matrix minus the true projection matrix on uncontaminated data. And we see that it is normal with mean zero and with a covariance matrix that depends on the expectation of the row-wise influence function multiplied by its transposed. So this is a rather typical result. But now, fortunately, because we have chosen our row function well, we can show that the efficiency of this method is quite good. There is a comparison. We made a comparison with a big simulation study. I will only say in words what the conclusion is. The conclusion is that when we have cell-wise outliers, we beat the row-wise robust methods. When we have row-wise outliers, we beat the cell-wise robust methods. And when both can occur, we beat all of the competitors, with the exception of macro PCA, but however, the new method has a much lower bias because of its higher efficiency. It's more interesting to look at a real data example. This is the ionosphere data that was used in previous publications by Barona and Yohai and other people. There are 225 cases and 32 variables. The data correspond to properties of electromagnetic signals sent into the ionosphere, which then they get reflected and measured by radar. And the variables are such that they can be plotted next to each other and you get interesting, meaningful curves. So the observed signals, the observed curves are here for 6 particular cases. For instance, this one and that one. And now, if we apply cell PCA, we also get the fitted curves, and these are the green curves. So for some of them, the green is almost the same as the purple, which was observed. So these are very nice cases with no outlyingness. And then for some of the others, we see deviations between the fitted and the observed. So there was something going on, and we will dig a little bit deeper into those cases. Cell PCA has a very nice byproduct, which is the imputed cases. And the formula for an imputed cell is this one. The imputed Xij cell is equal to the fitted cell plus a multiple of the observed cell minus the fitted cell. And this multiple is the cell-wise weight of that cell times the missingness indicator. That is 0 or 1. It's just 0 when we have a missing value, because then there is also no observed value. And then we get some special cases that explain this formula or illustrate this formula. When the cell is NA, then the missingness indicator is 0. And then the imputed cell is just the fitted cell, which always exists. When the cell is observed and the cell-wise weight is 1, then this factor is 1. And then the fitted cell cancels out. And so the imputed cell is just the observed cell. So when the observed cell has a weight of 1, we do not impute. We just keep the cell as it is. So the imputed cell is the original cell. In all other cases, we get something in between, because this product is always between 0 and 1. So each imputed cell lies between the observed cell and the fitted cell. And there is one very nice property, which is not obvious from the formula, that is that the orthogonal projection of the fitted case on the principal subspace, of the imputed case is the fitted case. So for the imputed data, it's basically true that the usual PCA model holds. And so an advantage or a way to use these imputed cases is if you then need to carry out a second step of your statistical analysis, and you only have a method that can deal with clean and complete data, then you can use the imputed cases for that. This is an example of the imputation. It's a small, it has small dimension, so we can show a plot, but it's really the cell PCA method that has been applied. It's an actual application. The observed points are the black points here. They were generated by Monte Carlo. And for most of the data points, the fitted cell, the fitted case is just the orthogonal projection. Oh, I forgot to say there are 3 dimensions in the data, and we fit one-dimensional subspace, which is this gray straight line. So for most of the cases, we just project orthogonally, but sometimes we have to impute first. So for case A, we first have to impute until we get to the orange point, and then we project orthogonally. And we see that this orange line is parallel to the first coordinate axis. So it is the first cell that has been imputed. The other cells stay the same. For case B, we see the orange line is parallel to the second coordinate axis. So it's the second cell that was imputed. And for point C, it was the third cell that was imputed. In the real data set, this is perhaps more revealing. We already had the purple line, which was the observed. The green curve was fitted, and the orange is always in between them. For the clean cases here, they are all very similar, but for the others, we get something in between. And we will focus on part of these curves on the next slide. So this is just variables 21 to 28. It's we zoomed in. And here we show the cell-wise weights. For the first 4 variables, the cell-wise weight was 1. And there we see that the orange curve, the imputed curve, is the same as the observed curve. For the last 2 variables here, the cell-wise weight is 0. And we see that indeed the imputed cells are the same as the fitted cells and quite different from the observed cells. And here we have weights that are cell-wise weights between 0 and 1. And indeed, the orange points are in between the purple and the green. There are visual characterizations of the data. To visualize outlying cells, we estimate the scale of the final residuals. So there are cell-wise residuals, that is a big matrix of the same size as the data matrix. And we can standardize the columns by their scales, and then we get the standardized residuals R tilde. And we can color in this cell map, we can color the residuals when the residual is small in absolute value. So this happens with probability 99% if the data are clean. Those cells we color yellow, meaning there's nothing special about them. When we get a residual that is much bigger and negative, we color them blue, meaning the observed value is much lower than what we would have expected. And red is when the observed cell has a higher value than what we would have expected. So the majority of cells is, of course, yellow, and there are some special cases. This is not a cell map for the entire data set with 225 rows, but only for the 6 cases that we showed in the plot. So these were the 6 curves that we saw. Some of them were clean, there was nothing special about them, and some are quite deviant. Then we have these circles on the right, and they correspond to the row-wise weight. They are in grayscale according to 1 minus the row-wise weight. So white means the row-wise weight is 1, and black means the row-wise weight was 0. And in between, we have the intermediate cases. There's also the enhanced outlier map. It plots the Euclidean norm of the standardized residual versus the scores distance that I explained before, which is based on the MCD. And the cutoff for the score distance is based on a chi-squared quantile. The cutoff for the standardized residual is based on a simulation because there's no analytic distribution for this. We basically use the xi naught and the projection matrix, and we simulate errors from the Gaussian distribution, and then we take the 99th percentile of those simulated data, and that's where we plot the dashed line. So we see that many of the cases are where they should be. These are the regular cases, and here are the bad leverage points, which have a big, which are far away in both directions. Here is a short real example. The Campi Flegrei is an active volcano field, part of which underlies part of the city of Naples, which is a very dangerous situation. And the temperature of this active volcanic field is measured on a daily basis by thermal infrared images in order to be able to predict an eruption. So we have in this data set 205 images corresponding to days between May and November 22. This is the outlier map, and we see there are a lot of regular cases, but there are some pretty outlying cases as well. And we look at just one of them, image 14. On the left, this is the actual image, where blue means colder, yellow means warmer, and red means hot. We also look at the part of the residual cell map corresponding to this frame only, and we see most of the cells are yellow, a few are red, but most of the cell-wise outliers are blue, meaning the temperature that we observed is lower than what we would have expected based on the linear model inside of the PCA model. And they are not visible in the raw image. So they deviate, but you could not see them if you just looked at the image. You need to do the PCA analysis. And what this is a known phenomenon. This is a blurred region due to condensation of water vapor. And so this is a kind of cloud. And this event happens mostly in the beginning and the end of the data set in the months where when it is a bit, when the air is more humid, and so there is a higher probability of forming these clouds. Conclusions for the talk is that the cell PCA method can handle case-wise outliers as well as cell-wise outliers and missing values. A novelty is that it minimizes a single objective function. A big advantage is that it assigns a weight to each case, but also to each cell, which helps the interpretation. The imputed cells can be used in further analysis. We were able to derive case-wise and cell-wise influence functions, and to show that the efficiency of this method is quite high, and there are graphical displays that help with the interpretation. There is a final message about the prize, the statistical prize that I sponsor. The first one was 2 years ago. This year, the winning contribution, the statistical innovation, is the false discovery rate and methods to control it. And the laureates are Yoav Benyamini, the picture in the middle, and the 2 other people are collaborators who did a lot to to advance the field, namely Ruth Heller and Danielle Giacottilli. There will be a ceremony in December in Leuven. Thank you for your attention.